Hello, welcome back. In this segment, I will discuss a digital signature scheme that was invented by ElGamal back in 1985. The scheme uses discrete logarithms as the underlying computational problem. We earlier talked about a cryptography system, encryption system in particular, that uses discrete logarithms as the underlying hard problem. So I will skip the encryption part. There are two parts in this paper, encryption part and digital signature part. I will focus on the digital signature part only. Section 3 is the main focus. And I'm going to follow the algorithm as given here, except one small notational difference. The paper uses alpha as a group generator, but I'm going to use G because we have been using G as a group generator. That's the only small difference. It's also easy for me to type G rather than alpha in my source code. Okay. All right, let's get started with the algorithm now, how the digital signature algorithm is implemented in ElGamal scheme. So we are working in a group Z star P, that's the group of interest. You can work in elliptic curve or anything else, but as long as you have a cyclic group, you can work with this. All right, so let's talk about discrete logarithm very briefly. The problem is given y, it is difficult to find x. Okay, of course, G is public, P is public, Y is public. Your goal is to find x, and that seems to be a hard problem. What is the public key in this context is Y, G, and P. The private key is x. All right, that's the discrete logarithm problem. So now let's get back to the digital signature problem. Digital signature has two things. One is signing a message, and the other is verifying the message. So let's talk about sign. In the context of ElGamal, if your goal is to sign a message M, you're going to generate two numbers R and S such that G power M is same as Y power R times R power S. That is your goal. The numbers M, R, and S are all group elements, so they must be part of Z star P. Now the question is, how do I find R and S? Okay, because the verification requires R and S and M. You can imagine M itself is not confidential. That's the reason why you're passing M in clear to the verifier. Okay, how can I find R and S? In order to find R and S, we proceed as follows. We generate a random number K first, and then we apply G power K in mod P. So I'm not writing mod P again and again unless it's a different mod. You can imagine it is mod P. So R is randomly generated because K is randomly generated. Okay, G power K mod P will give you an R. Okay. Now we go and put it in this equation. So we know G power M is equal to, what is Y? Y is G power X, right? So it is G power XR. And what is R? R is G power K. So now your left hand side G power M, right hand side G power X times R plus K. This means the exponents must be equal in mod P minus 1. That's important. The exponents must be congruent in mod P minus 1. The reason is that the group Z star P, the order of the group is P minus 1. Oh, I forgot an S here. All right, so we know R because we just generated it, and we know M, that's the input. We know K, we picked K here. This is the K that you pick every time you sign is called, a K is picked. So we can now solve this equation to find S, right? So if you just rearrange this, you can say S is equal to M minus XR into K inverse. Okay, now I have to be careful. One more thing I need to tell you. K inverse in mod P minus 1. So the careful part is that K inverse must exist, right? Otherwise, you can't solve this equation. So K must be relatively prime to P minus 1. Okay, that's another constraint. When you generate a K, not any K cannot be used. So K must have this property that, so if that is true, you can find a K inverse using extended Euclidean algorithm, for example. We talked about it earlier. Okay, so we know M, we know R, we just generated here. We know K, we can apply extended Euclidean algorithm to find a K inverse. So we are able to find S. So we return, the signature basically returns two things, R and S. It's the output that comes out from the signature algorithm. So I hope you got the idea of how a message is signed. As you can see, in order to sign a message, you would need your private key as input. Okay, suppose you are the owner who want to sign a message, you need the private key. There are some attacks where you can do some existential forgery without having the private key, but that is something persistent in many crypto systems. For now, assume that you would need a private key to sign your message. Okay, all right. Okay, let's talk about verification. Verify will take M or S as input, and will check whether G power M is same as Y power R times R power S. Okay, everything is public. R is public, S is public, M is public, G, Y is also public anyways. So if these two are equal, then you say, yeah, it's a good signature. Otherwise, you say it's a forgery. That is basically it. One thing you may wonder is, where is the discrete logarithm used here? So if discrete logarithm is easy, then this is broken immediately, right? Because you would be able to find from y, x, from r, you will be able to easily find k. So you can generate any signature you want for any message, of course. That is obvious immediately. But it doesn't mean that breaking this scheme is same as breaking discrete logarithm problem. Maybe there is a way to break the digital signature problem, meaning generate a signature without having a private key, yet it's difficult to find the private key itself. Okay, that's something we are not sure whether these two are equivalent. Okay, but there is one more interesting question, at least one interesting question. This k that I talked about, this k must be unique for every time you wanted to sign a message. Even if it is the same message, you need to generate a unique k. What happens if the k is not unique? Let me explain what happens in that case. In that case, the attack is as follows. This happened back in 2010 when Sony was hacked. The same k was used. What you're going to do is look at this equation carefully, right? Let me write it as equation m equal to, I'm not going to use congruence for now, but you can imagine it's congruence. M is equal to x times r plus k times s, right? Let's assume you observe two messages. So it will be m1 and you have m2, which is going to be same private key, but r2 and k s2. I'm using the same k, which is wrong, right? Every time sign is called, a new k has to be generated, but I'm using the same k by mistake. Let's assume this code was written only once outside, and they're using it as a global variable. Well, in that case, what will happen is that now you see, R1, R2, right? Well, R1, R2 is same as, they are also equal anyways, because k is fixed. So how many unknown variables you have? You have only x and k as unknown. The rest are all known. So you have two equations with two unknown variables. You know how to solve that from basic algebra. You can just subtract, multiplicative inverse, and so on. You will be able to easily find x from these two equations. So we should never use the same key k. It's not exactly key, but the same random number k. Whenever we apply ElGamal scheme, the R must be unique. Okay, so R must be unique. There should be no collusion. Otherwise, you are able to leak X. Otherwise, somebody can extract private key X from the public key. Okay. All right. There are more attacks over time people found. It's possible even to generate a signature without having the private key X. Some of the attacks are easy to stop by using hash function of m. Here we are directly applying m, right? M is directly used. If you use hash of m, some of the multiplicative properties and things like that can disappear because the hash function behaves like a random function. That's the belief. All right, let me now show you very briefly the Python implementation I have put together for this idea. Of course, you would need a group generator to generate the public parameters p, g, y, and x is considered private. And to digitally sign a message, you need a message, you need your private key, and the public parameters p and g. As I said earlier, we need to find a good k, randomly select a k until j is relatively prime to p minus 1, the loop runs. As soon as a good k is found, we can go ahead and compute the k inverse, and then we solve for r and s, as I have shown here. R and s are computed here, and the digital signatures R and S. To verify, it's extremely simple. You just check whether g power m is same as y power r times r power s, as I shown on the whiteboard. So here is the little demo. Suppose Bob wants to sign a message using his private key x. He will first generate his key, keeps his public key public, private key private. Bob signs a random group element for demo purpose. He randomly picks an element from the group, and he uses his private key to sign the message. As you can see, x. He gets R and S. He publishes R and S and M to the world. Now anyone can check whether this is a valid signature by using Bob's public key. As you can see, we are using Bob's public key parameters. P, G, M are all public. Of course, R and S is public, M is public. So we are verifying everything using public data. That's all.